Okay, hi. This is, what was the problem number?
It is
6.51.
For 6.51, this is the problem where we have a sled going up a hill and then back down. We have a few givens. We have the mass of the sled being 5 kilograms. We have the angle of the hill that the sled is on as being 25 degrees. We have the coefficient of friction for snow being 0.06. We have velocity initial, so the speed going up the hill initially being 9 meters per second. And we also know that our velocity when we reach the peak of the hill is going to be 0 meters per second. So the issue for this problem is that it's 2 parts, so we need to find the AX going up the hill. We also need to find the change in height vertically of the sled going up the hill. We also need to find velocity final when it goes back down the hill. And in order to find that, we need to find AX going back down the hill. So just to draw our scenario and set up a coordinate system, we're gonna, oh, that's very steep, but you get the idea. So we have, so the ramp is at degree theta. We have our sled, which will be represented by this point. We have force gravity, which is pointing straight down into the hill. Oh, shoot. We have force normal, which is pointing out from the hill. And then we have force friction, which is resisting the movement of the sled going up the hill, so it's going to be in the opposite direction. So let's set up our sum of forces. So the sum of the forces is going to be equal to MA. In this case, our forces are going to be force gravity, force normal, force friction. So let's set up our vectors. So FG is only going in the negative y direction, so that's going to be negative FG. Force normal, it's going to be pointing, oh shoot, no. To break down the, actually, sorry, because of our coordinate system, actually FG is going to have 2 components, one in the negative y direction and one in the negative x direction. Then we have force normal, which will be only pointing in the y direction. So that's going to be force normal. And then we have force friction, which is only going to be in the negative x direction. And then MAX and MAY. From here, we know that force friction is equal to mu force normal. So when we translate this, we can set force normal to be negative mu force normal. Force normal we don't know yet. And then the y component of force gravity is going to be the cosine of that, so it's going to be negative mass gravity cosine theta, and then the x component, which is pointing in the same direction as the force friction, is going to be negative mg sine theta, because it is the opposite of this angle. So, and then zeros everywhere else. We also know that it's not accelerating in the y direction, it's not falling off the hill, so we know that's 0. So we have MAX. So we'll use this to find AX. So from here we know that negative mg sine theta minus the coefficient of friction times force normal is equal to 0. So that means force normal is going to be the same as mg sine theta. And for the second, or for the other formula in the x direction, or no, wait, did I confuse something? Oh, I forgot the mu, that's all. And then in the x direction, we have negative, shoot, what did I write wrong? That's, oh no, this is equal to max, sorry. That's not equal to 0. And then for the y direction, we have mg cosine theta plus force normal is equal to 0. So we know force normal, I skipped a step, that's why. I thought it was the wrong formula, so cosine theta. So we can use this, this equation for force normal and plug it into here. So we now have mg sine theta minus mu times mg cosine theta is equal to max. We can divide both sides by m. Because each of these terms have m inside it, we can distribute it out. So we now have negative g sine theta minus mu g cosine theta is equal to a sub x. This is going up the hill. So from there, we can plug in our knowns in order to get ax is equal to negative 9.8 meters per second squared times sine 25 minus our force, our coefficient of friction 0.6 times 9.8 meters per second squared, and then multiply that by cosine 25. And when you plug this into a calculator, so ax going up, you get negative 4.67 meters per second squared. So we have the ax going up the hill, and so from using that, we now need to figure out our change in height. And in our x direction, shoot, that's a bad example. Any change in x, so like say if our change in x, because this is our x direction, is the hypotenuse of the hill, then in order to find our change in height, it's going to be change in x, so change in x sine theta is going to be equal to our change in height. So from there, we need to find our change in x, and our change of x we can use by using our third kinematic formula, which is velocity final squared, velocity initial squared plus 2a change in x. This will be our up direction. And then we need to isolate that, so we move velocity initial to the other side of the equation. And then we divide by, the change in x by 2ax. Good. This VF is actually going to be our V height, so we can plug in all our numbers now. So we, we have that, so our change in height is just going to be this times sine theta. So our change in height is going to be equal to 0 meters per second squared minus 9.9 meters per second squared divided by 2 times this number that we got down here, negative 4.67, and then we multiply that by sine 25. And then when we plug that in, we get change in height being equal to 3.67 meters. So we solve part A of the problem. Now we need to solve part B. Now the issue with part B is now because the sled is going back down the hill, force friction is actually going to be pointing in the opposite direction. And then we have, so force friction is now going to be pointing in the positive x direction. Now thankfully, because of this formula here that we have for ax, the component that we got for this, all we need to do is just turn that negative, or is make this part positive. So we now have MAX going down the hill being equal to negative mg sine theta plus nu force normal, which we have force normal being mg cosine theta. And because of the m's, we can cancel those all out. So MAX down is going to be equal to negative g sine theta x plus mu g cosine theta. And then when we do that, we get the value of negative 3.6 meters per second squared. We can now use this to plug into the same third final formula, because we know that velocity initial is going to be 0. So we have velocity final is equal to velocity initial plus 2a down change of x. Our change of x is going to be the exact same going down the hill because we have to reach the bottom of the hill. So that's going to be our, oh crap. For this part of the problem, I forgot the change of x. That is going to be, oh. No, okay. Oh, the change of x was derived up here. So our change of x was, our change of x up here was equal to what value? Does anyone have that on hand? Is it on here? We can take this part of the formula without the sign. Oh, that would just be that without the sign. Sorry about that. Oh, this part was equal to 8.67 meters. So we know this value. Sorry about that delay. So then we just want square root each side. So we have velocity final being equal to the square root of velocity initial squared plus 2ax down, change in x. So now that we plug that in, we have this. We have 0 meters per second squared because our velocity initial going back down the hill, we had to wait at the top. And then we have 2 times our negative 3.6. Negative 3.6 meters per second squared, and then multiply that by our change in x, that was 8.67. And then when we plug that all together, we get velocity final being equal to 7.91 meters per second. And that's the end of part B.